Need to add logging, progress updates, or user interaction to your FastMCP tools without cluttering your function signatures? You'll see how the context object gives your tools direct access to FastMCP's advanced features, like logging, progress reporting, and even real-time user input, just by adding a single typed parameter. Here, the clean, dependency-injected way to supercharge your tools while keeping them simple. From FastMCP, import FastMCP. Context. MCP equals FastMCP. Name equals context demo. @MCP, tool. Async def process file URI. SDR-CTX, context. SDR. Processes a file, using context for logging and resource access. Hash context is available as the CTX parameter. Return processed file. This demonstrates the dependency injection pattern combined with contextual resource access in RPC frameworks. The context object acts as an implicit parameter container, providing tools with access to cross-cutting concerns like logging, progress reporting, and resource management without explicit parameter passing. What makes this distinctive is how it cleanly separates business logic from infrastructure concerns while maintaining full type safety through Python's type hints. The pattern works by treating context as ambient capability rather than explicit dependency. Functions declare their need for context via type hints, and the framework automatically injects the appropriate instance at runtime. This creates a declarative boundary where tools focus purely on their core logic, while the framework handles the plumbing for capabilities like user elicitation, state management, or LLM sampling. The Async-first design ensures non-blocking access to these capabilities, maintaining performance even during I/O operations. This approach solves the common problem of parameter explosion in RPC systems, where tools would otherwise need dozens of parameters for logging, auth, and progress tracking. It's particularly valuable in AI integration scenarios where tools must remain simple for model consumption, yet still need access to rich runtime capabilities. The trade-off is slightly reduced explicitness about dependencies, but the benefit is dramatically cleaner tool interfaces and easier testing through mock contexts. Let's break it down line by line. From FastMCP, import FastMCP. Context. Imports FastMCP, the core class for creating AI-callable tools, and context for tool execution metadata like logging and progress reporting. These are the foundational components for building FastMCP toolchains. MCP equals FastMCP. Name equals context demo. This initializes the FastMCP instance, the central orchestrator for AI-callable tools. The name parameter identifies this toolset in logs and error reporting, enabling better debugging. All tool functions register with this MCP instance via decorators. @MCP, tool. Async def process file URI. SDR-CTX, context. SDR. Processes a file, using context for logging and resource access. This defines an AI-callable tool using FastMCP's decorator pattern. The @MCP tool decorator exposes this function to AI models, while the CTX context parameter provides logging and resource access, a standard requirement for all FastMCP tools. The async definition enables non-blocking execution, critical for scalable AI workflows. Hash context is available as the CTX parameter. Return processed file. This demonstrates the FastMCP tool signature pattern. All tools must accept a context parameter for logging, progress reporting, and resource access, even if unused. The simple return shows the minimal viable implementation while maintaining the required interface. FastMCP context pattern. The context object in FastMCP 2 provides request-scoped utilities like logging, progress reporting, and resource access, injected automatically into your tool functions. Each request gets a fresh context instance, so never assume state persists between calls. The type hint can be context none or use annotated for optional context handling.
The context that knows everything forgets everything.